Hello, and a warm welcome to Heavenly Sleep Stories. If you're new here, this is a place where we explore the deepest mysteries of the universe, all designed to intrigue your mind and soothe your spirit. If you find comfort in these grand cosmic journeys, we would be deeply honored if you'd consider subscribing to our channel and clicking the bell icon. Your support helps us continue bringing these stories to you. Today, we embark on our most ambitious journey yet, an exploration of the most enigmatic and powerful objects in the cosmos, black holes. For the next hours, we will unravel their secrets, from their violent birth in the heart of dying stars to their role as the architects of galaxies. We will dissect their terrifying anatomy, from the point of no return at the event horizon to the singularity, where all known laws of physics break down. We will relive the great hunt, from the first suspected black hole, Cygnus X1, to the planet-sized telescope that captured the first ever image of one's shadow. We will dive into the cutting-edge science that suggests they may not be eternal prisons, but could slowly evaporate, posing the greatest paradox in modern physics. And we will not shy away from the mysteries that fuel our imagination. We will explore the tantalizing theory of wormholes, the speculative technologies that could one day harness their power, and the compelling conspiracy theories that ask, could they be stargates, or even the remnants of other universes? This is more than a documentary. It is a story of cosmic creation and destruction, a testament to human curiosity, and a humbling look into the darkest mirrors of the universe. So, find a comfortable space, and let us begin our descent into the infinite tapestry of the cosmos. Woven with brilliant stars and swirling galaxies, there exist monsters. They are the ultimate paradoxes. Regions of space where gravity has become so overwhelmingly powerful that nothing, not even a single particle of light, can escape their grasp. They are the perfect hiding places, the ultimate secrets. And yet, they are also some of the most energetic, influential, and important objects in the entire universe. How can something that emits no light shine so brightly in our understanding of physics? How can a void shape the very fabric of the cosmos? This is the central, captivating mystery of the black hole. Our story begins not with a telescope, but with a mind. In the early 20th century, Albert Einstein gave us a new theory of gravity, a radical reimagining of the universe he called general relativity. His equations described gravity not as a force, but as a warp in the very fabric of space and time. And within those beautiful, complex equations, a ghost appeared. The mathematics hinted at the possibility of points in space where matter could be compressed into an infinitely dense knot, a singularity, surrounded by a boundary from which there was no return. But Einstein himself was deeply skeptical. He believed that while the math was sound, nature would somehow find a way to prevent such a bizarre and terrifying object from ever truly forming. He once wrote, "Black holes are where God divided by zero," a poetic way of saying they are points where our mathematics and our physics simply break down, yielding nonsensical, infinite answers. In a way, the greatest scientific mind of his generation believed his own theory had revealed a cosmic impossibility. Yet, the ghost in the equations refused to fade. It lingered, a tantalizing and frightening prediction, waiting for the world to catch up. It was a theoretical phantom, a dark prophecy written in the language of mathematics, challenging future generations to prove whether it was a flaw in our understanding, or a truth about reality that was stranger than anyone could have dreamed. This prologue is the story of that phantom. It is the prelude to our descent into the heart of darkness, a journey that will take us from the death cries of massive stars to the edge of reality itself. The monsters are real, and their silence is the most profound sound in the universe. The fiery wombs of darkness, a star's suicide. To understand the birth of a black hole, we must first witness a death. A death on a scale so colossal, it forges the elements of life itself, and in its final, cataclysmic moment, gives birth to the ultimate cosmic paradox. This is the story of a star's life, and its spectacular suicide. For millions, even billions of years, a massive star exists in a state of perfect, violent balance. In its core, a continuous thermonuclear furnace rages, fusing hydrogen into helium, releasing unimaginable energy. This outward pressure of radiation pushes relentlessly against the star's own immense gravity, which is constantly trying to crush the star inward. It is a stalemate of cosmic forces, and this equilibrium is what makes a star shine steadily in the night sky. But this balance is temporary. As the star ages, it begins to fuse heavier and heavier elements in its core, helium into carbon, carbon into oxygen, and so on, like a layered onion of nuclear fusion. In its final days, it forges elements like silicon and magnesium. This process is the universe's primary alchemist. The very iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in the nuclear hearts of long-dead, massive stars. We are, literally, made of stardust. Then, the star creates iron. And iron is the ash of nuclear fusion. Unlike previous elements, fusing iron does not release energy, it consumes it. The star's central engine, which has run tirelessly for eons, suddenly sputters and stalls. With the outward pressure from fusion cut off, the star's battle is lost. Gravity, after a lifetime of being held at bay, wins in an instant. What happens next is one of the most violent events in the universe. The core, no longer supported, collapses at a quarter the speed of light. The outer layers of the star, suddenly without a foundation, come crashing down and then rebound in a titanic shockwave. The star explodes in a supernova, an eruption of energy so bright it can, for a few weeks, outshine an entire galaxy of 100 billion stars. It is the star's final, glorious scream, scattering the newly forged elements of life across interstellar space, seeding future generations of stars and planets. But while the outer layers are being blasted into space, the core's collapse continues unabated. If the remaining core is sufficiently massive, roughly 2 to 3 times the mass of our Sun, no known force in the universe can stop its descent. It shrinks from thousands of miles across to a mere dozen in seconds. The protons and electrons are crushed together to form neutrons, creating for a moment an impossibly dense neutron star. But if the mass is too great, even the neutrons cannot withstand the pressure. The collapse continues, accelerating, until the entire mass of the core is compressed into an infinitely small, infinitely dense point, a singularity. At the moment of the singularity's creation, something else emerges in the fabric of space-time around it. A boundary forms, an invisible sphere marking the point of no return. This is the event horizon. It is not a physical surface. You could not touch it. It is a gravitational threshold. Once anything, a particle, a spaceship, a photon of light, crosses this boundary, its fate is sealed. It will be drawn, irresistibly, to the singularity at the center. The black hole is born. From the fiery, luminous death of a star, the darkest object in the universe has emerged. And so, from the ashes of a stellar giant, a monster awakens. But what is the nature of this beast? What is its anatomy? To understand its power, we must now venture closer, to dissect the black hole itself. Anatomy of a black hole. The birth of a black hole is a violent, chaotic event, but the entity that emerges is a thing of stark, almost elegant, simplicity. According to the fundamental principles of general relativity, a black hole in a pure state can be described by just 3 properties: its mass, its electric charge, and its spin. Everything else, every detail about the matter that formed it, the star it once was, the planets it may have consumed, is lost, scrubbed away. This is the no-hair theorem, suggesting that black holes are the universe's ultimate bald entities, their complex pasts hidden forever. But around this simple core lies an architecture of such extreme physics that it defies human intuition. At the very center of the black hole lies the singularity. This is the point of infinite density, where all the mass that has crossed the event horizon is crushed into a volume of 0 size. Here, the curvature of spacetime becomes infinite, and the laws of physics, as we know them, completely break down. General relativity, which predicts the singularity's existence, cannot describe its conditions. It is a place where the concepts of space and time themselves cease to have any meaningful definition. The singularity is not a physical object you could touch. It is a mathematical and physical absurdity, a tear in the fabric of reality, representing the ultimate frontier where our current understanding must be replaced by a theory of quantum gravity. Surrounding this enigmatic center is the event horizon, the black hole's defining feature. This is not a solid surface, but a one-way membrane in the fabric of space-time, a point of no return. Think of it as a river flowing towards a waterfall. For a long time, you can paddle against the current and escape. But once you cross the edge of the waterfall, no amount of effort can bring you back. The event horizon is that edge. Its size is determined by the black hole's mass, and it is described by the Schwarzschild radius. For any given mass, if you could compress it within its corresponding Schwarzschild radius, it would collapse into a black hole. For our Sun, this radius is a mere 3 kilometers. For Earth, it would be just 9 millimeters. Once this boundary is crossed, all paths through space-time lead inexorably inward, toward the singularity. Not even light, the fastest thing in the universe, can travel a path that leads back out. But the simplicity ends for black holes that are spinning, and most are believed to spin incredibly fast, a legacy of the angular momentum of the collapsing star and the matter it consumes. A rotating black hole, described by the Kerr solution, has a much more complex and dynamic structure. Outside the event horizon lies a region called the ergosphere, an oblate spheroid that is flattened at the poles. Within the ergosphere, space-time itself is dragged around the black hole at such a phenomenal rate that it is impossible for any object to remain stationary. This effect, known as frame dragging, is so powerful that it forces everything to move with the rotation of the black hole. The ergosphere is a region of immense energy, and in theory, it is possible to extract energy and mass from it via the Penrose process. A particle could enter the ergosphere and split in two, with one part falling into the event horizon and the other escaping with more energy than the original particle had. In this way, we could, in principle, steal rotational energy from the black hole it is actively feeding. The most visible and violent part is the accretion disk. This is a colossal, superheated whirlpool of gas, dust, and stellar debris spiraling inward at velocities approaching the speed of light. As this material is pulled inward, it is compressed and heated to temperatures of millions of degrees by immense frictional and tidal forces, causing it to glow intensely across the electromagnetic spectrum, from radio waves to powerful X-rays. It is this luminous, frenzied maelstrom, not the black hole itself, that allows us to detect these dark objects. The physics within an accretion disk is a complex dance of magnetohydrodynamics, where magnetic fields thread through the plasma, transferring angular momentum outward and allowing matter to spiral inward. The inner edge of the accretion disk, where material makes its final plunge toward the event horizon, is a laboratory for studying strong field gravity. From the poles of many actively feeding supermassive black holes erupt the most powerful and enigmatic structures in the universe, relativistic jets. These are colossal, tightly collimated beams of ionized matter and radiation that shoot outward at nearly the speed of light, often extending for thousands or even millions of light-years beyond their host galaxy. The exact mechanism that forms these jets is still a topic of intense research, but it is believed to be powered by the black hole's spin and its immense magnetic fields, which are twisted and amplified by the rotating accretion disk. These magnetic fields act like a gigantic particle accelerator, funneling material from the inner disk and launching it into the intergalactic void. These jets can transport phenomenal amounts of energy, regulating star formation in the surrounding galaxy and heating the intracluster medium, effectively putting a cap on how large a galaxy can grow. They are a stark reminder that while black holes are defined by what they pull in, their influence is exerted across cosmic distances through what they violently expel. Finally, there is the photon sphere, a region of pure light and shadow that defines the black hole's visual appearance. This is a spherical shell surrounding the event horizon at a distance of 1.5 times the Schwarzschild radius, where the gravitational pull is so strong that photons of light are forced to travel in unstable orbits. They are not falling in, nor are they escaping. They are trapped, circling the black hole forever. This region is what creates the shadow that the Event Horizon Telescope famously imaged. The bright ring of light we see is from photons that have skimmed the photon sphere and just barely managed to escape, bent by gravity on their long journey to our telescopes. The dark void within that ring is the shadow of the event horizon, magnified by gravitational lensing, a silent testament to the point of no return. It is the closest we can come to taking a picture of the unseen. How we find the invisible. The existence of black holes, for decades, remained a beautiful but unproven theoretical conjecture. How does one hunt for an object that, by its very nature, emits no light and hides behind an impenetrable veil? The story of their discovery is a masterpiece of indirect detection, a testament to human ingenuity in observing the effects of an unseen actor on the visible cosmic stage. Astronomers became detectives, piecing together the presence of a ghost from the terrified behavior of everything around it. The first compelling candidate for a black hole emerged not from a void, but from a brilliant source of X-rays in the constellation Cygnus, known as Cygnus X1. In the early 1970s, meticulous observations revealed that Cygnus X1 was not alone. It was part of a binary system, locked in a gravitational dance with a massive blue supergiant star. By studying the orbit of the visible star, scientists could calculate the mass of its invisible companion. The result was staggering. The unseen object had a mass estimated at over 10 times that of our Sun, far exceeding the theoretical maximum for a neutron star. Such a massive, dark, and compact object could only be one thing: a stellar mass black hole. But how was it seen? The black hole itself was dark, but its immense gravity was pulling streams of gas from its massive companion. As this stolen gas spiraled down into an accretion disk, it was heated to millions of degrees, glowing with intense X-rays before vanishing forever across the event horizon. Cygnus X1 became the first smoking gun, a dark heart revealed by the screams of the material it was consuming. This method of detection through binary companions became a standard tool, but it was limited to finding black holes with visible partners. To find the isolated monsters, and especially the supermassive ones at the centers of galaxies, a different technique was needed: observing the gravitational influence on stars. At the very heart of our own Milky Way galaxy, astronomers began tracking the orbits of individual stars around an invisible, compact radio source known as Sagittarius A star. For years, they painstakingly mapped the paths of these stars, and what they found was breathtaking. These stars were whipping around this invisible point at speeds of thousands of kilometers per second, executing incredibly fast, tight orbits. Using Kepler's laws, the calculation of the central mass was inescapable. Lurking at the center of our galaxy is a supermassive black hole with a mass of about 4 million suns, all contained within a region smaller than our solar system. The frenetic dance of these stars provides the most direct and compelling evidence for the existence of this lurking leviathan. Though more subtle tool is gravitational lensing, a dramatic confirmation of Einstein's general relativity. According to the theory, a massive object warps the spacetime around it, bending the path of light much like a glass lens. A black hole, with its extreme gravity, acts as a powerful natural lens. When a black hole passes in front of a more distant background star or galaxy, it can distort, magnify, and multiply the image of that background object into arcs and rings of light, known as Einstein rings. This phenomenon not only allows us to infer the presence of the intervening black hole, but also to map its distribution of mass, including the mysterious dark matter that often surrounds it. It is a cosmic mirage, a distortion of reality that reveals the shape of the invisible. The most iconic moment in the hunt for black holes arrived on April 10, 2019, with the announcement by the Event Horizon Telescope collaboration. The EHT was not a single telescope, but a global network of radio observatories spanning the Earth, from the mountains of Hawaii to the high deserts of Chile, from the South Pole to the peaks of Spain. Using a technique called very long baseline interferometry, these disparate telescopes were synchronized to act as a single, planet-sized observational instrument, achieving an angular resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. The target was the supermassive black hole at the heart of the galaxy M87, a behemoth 6.5 billion times the mass of our Sun. The image they produced was not of the black hole itself, but of its shadow, the dark silhouette of the event horizon set against the brilliant, lensed glow of its surrounding accretion disk. This glowing ring of light, asymmetrical due to the incredible rotation of the disk and the Doppler effect, matched the predictions of general relativity with stunning accuracy. It was a direct image of the abyss, a monumental achievement that transformed black holes from mathematical abstractions into observable cosmic entities. Perhaps the most revolutionary detection method came online on September 14, 2015, when the LIGO observatories detected a signal designated GW150914. For a fraction of a second, the fabric of spacetime itself rippled as two black holes, one about 36 and the other 29 times the mass of the Sun, spiraled inward and merged in a galaxy 1.3 billion light-years away. The signal was a chirp, a rising frequency and amplitude that perfectly matched the predictions of Einstein's equations for such a cataclysmic event. This was the first direct detection of gravitational waves, opening an entirely new window on the universe. Unlike light, gravitational waves pass through matter unimpeded, allowing us to listen to the otherwise invisible, dynamical universe of compact objects. Through these observations, we have discovered a whole population of stellar mass black holes, and we have confirmed that such binary black hole systems not only exist but are common, their mergers seeding the universe with heavier black holes. However, such profound discoveries inevitably attract skepticism and conspiracy. In the wake of the LIGO detections, a minority of physicists and many skeptics have raised questions. They point to the uncanny similarity between the signals and the computer-generated templates, suggesting the data may have been inadvertently, or even intentionally, cleaned to match expectations. Others note the curious timing of the first detection, coming just after the observatory was upgraded and as the team was under pressure to produce a result after decades of funding. They argue that the signals are too perfect, that the random noise of the universe should create more anomalies, and that the entire field could be a case of collective confirmation bias. While the scientific consensus, reinforced by multiple subsequent detections, firmly supports the reality of gravitational waves, these theories persist in the fringes, a reminder that even our most celebrated discoveries are scrutinized in the court of public and scientific opinion. The hunt for the invisible, it seems, is also a battle against the black hole zoo. The term black hole often conjures a singular image, but in reality, these objects come in a staggering variety of sizes and origins, forming a veritable cosmic zoo. This classification is not merely academic. It represents fundamental differences in formation, behavior, and influence on the universe. From relics of the Big Bang to the architects of galaxies, the diversity of black holes reveals a cosmos far more complex and dynamic than we once imagined. The most common and readily understood inhabitants of this zoo are the stellar mass black holes. These are the remnants of massive stars that met their end in a supernova explosion, as detailed in our previous chapter. Ranging from approximately 3 to 100 times the mass of our Sun, they are scattered throughout the galaxies, often leading solitary lives or, as we saw with Cygnus X1, orbiting a companion star in a binary system. Their detection relies on their interaction with this companion or, more recently, through the gravitational waves they emit upon merging. They are the ghosts of dead stars, the baseline population of darkness in the cosmic ledger. Yet, even within this category, mysteries persist. The recent discoveries by gravitational wave observatories have revealed a surprising number of black holes in the so-called upper mass gap, between 60 and 120 solar masses, a range theoretically difficult to achieve through standard stellar collapse. This suggests that many of these black holes may be second-generation objects, themselves the products of earlier mergers, hinting at a rich and violent evolutionary history in dense star clusters. At the other end of the spectrum reside the supermassive black holes, the true titans of the cosmos. These are not the corpses of individual stars, but the foundational keystones of entire galaxies. Residing at the very centers of galaxies, including our own Milky Way with its 4 million solar mass Sagittarius A*, these behemoths can weigh in at millions to billions, and even tens of billions, of times the mass of our Sun. Their existence is now considered a universal feature of galaxy formation. However, their origin presents one of the most significant puzzles in modern astrophysics, the seed problem. How did objects so immense form so quickly? Observations of incredibly bright quasars, active supermassive black holes, in the very early universe indicate that they were already in place when the cosmos was less than 1 billion years old. There is simply not enough time for a stellar mass black hole to grow to such a staggering size through accretion alone. Several theories attempt to explain this. One posits the direct collapse of enormous, pristine gas clouds in the early universe, bypassing the star formation stage entirely to create a heavy seed black hole of tens of thousands of solar masses from the outset. Another, more exotic theory suggests that these seeds were formed from the dense conditions following the Big Bang or from the collapse of enormous, hypothetical population 3 stars, the universe's first generation of stellar giants. The growth of these seeds, through frantic feeding and a frenzy of mergers, built the galactic monarchs we observe today. Their gravitational influence is so profound that they dictate the dynamics of their host galaxies, regulating star formation and, through their relativistic jets, injecting energy into the intergalactic medium. They are not mere residents of galaxies. Between the stellar and the supermassive are the elusive intermediate mass black holes, IMBHs. For decades, they were the missing link of the black hole family, predicted by theory but frustratingly difficult to confirm. With masses ranging from a few hundred to a few 100,000 solar masses, they are too small to power the brilliant quasars of the early universe yet too large to form from a single collapsing star. Their suspected habitats are the dense cores of globular clusters, ancient, spherical swarms of stars, and the disrupted nuclei of small galaxies that have been cannibalized by larger ones. Evidence for their existence has been mounting slowly. Astronomers have detected ultraluminous X-ray sources, ULXs, in nearby galaxies, whose brightness suggests an object that has surpassed the theoretical limit for accretion onto a stellar mass black hole, pointing to a more massive central engine. Furthermore, the gravitational wave signal GW190521, detected by LIGO and Virgo in 2019, was from the merger of two black holes of 85 and 66 solar masses, creating a final black hole of 142 solar masses, firmly in the intermediate mass range. This discovery proved that such objects do form and merge in the universe. Finding more IMBHs is crucial, as they are the hypothesized building blocks that merge to form the supermassive black holes, and their study could finally solve the seed problem. Venturing into the realm of the truly theoretical, we encounter the concept of primordial black holes, PBHs. First proposed by Stephen Hawking and others in the early 1970s, these are not born from dying stars but from the extreme densities and pressures of the universe's very first moments after the Big Bang. Tiny, random fluctuations in density in that seething primordial soup could have caused regions to collapse directly into black holes. The fascinating aspect of PBHs is their potential mass range, which could span from the infinitesimally small, millions of tons, compressed into a size smaller than a proton, to many times the mass of our Sun. This opens up a wild and speculative frontier. Some theorists have proposed that the mysterious dark matter, which makes up 85% of the universe's matter and whose nature remains utterly unknown, could be composed of a vast swarm of asteroid mass rays have narrowed the possible windows where PBHs could account for all dark matter. The idea remains compelling. Even more speculatively, the evaporation of the very smallest PBHs, a process known as Hawking radiation which we will explore in a later chapter, could be responsible for the enigmatic, high-energy gamma-ray flashes we observe across the sky. They are ghosts from the dawn of time, and their potential discovery would revolutionize our understanding of both cosmology and particle physics. This bestiary of darkness would not be complete without addressing one of the most persistent and captivating conspiracy theories in astronomy: the idea of a hidden, planet-sized object, sometimes called Planet X or Nibiru, lurking in the outer solar system. While most often imagined as a planet, a more scientifically intriguing, though still highly speculative, variant suggests this object could be a primordial black hole. The theory stems from observed gravitational perturbations in the orbits of distant trans-Neptunian objects, which some astronomers have argued could be explained by the presence of an unseen, massive body. While a planet is the most discussed candidate, a grapefruit-sized primordial black hole with a mass of 5 to 10 Earths would exert the same gravitational pull. This would explain why our telescopes have seen no reflected sunlight from such a massive object. It is a fringe idea, with the vast majority of the astronomical community finding the planetary explanation more likely and the evidence itself still debated, but it captures the imagination. It proposes that a relic from the birth of the universe could be hiding in our own cosmic backyard, a dark, miniature monster silently orbiting in the frozen depths beyond Pluto, its presence betrayed only by the subtle tug it exerts on the frozen worlds at the edge of our sun. The physics of the impossible. Venturing beyond the mere classification of black holes, we now cross a threshold into a realm where physics as we know it is stretched to its absolute breaking point and beyond. The environment surrounding a black hole is a natural laboratory for the most extreme phenomena in the universe, where the familiar rules of reality are warped, twisted, and rewritten. To understand a black hole is to take a journey through a looking glass into a world of terrifying and wondrous possibilities. The most visceral and gruesome fate that awaits any matter crossing a black hole's event horizon is a process with a deceptively simple name: spaghettification. This is the direct and brutal consequence of tidal forces. Gravity's strength is inversely proportional to the square of the distance, meaning that if you were falling feet first towards a stellar mass black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. The difference is not a gentle tug, it is an overwhelming force. You would be stretched lengthwise into a long, thin stream of atoms, resembling a piece of spaghetti. Simultaneously, the sides of your body would be compressed inward by the same tidal forces. For a supermassive black hole, the event horizon is so far from the singularity that the tidal forces there are much weaker. You might actually cross the event horizon intact, a quieter, more insidious entry into the abyss before the inevitable spaghettification occurs deeper within. This process is not limited to astronauts. It applies to any object, from asteroids to gas clouds, and the intense stretching and compressing are a primary source of the heat that makes accretion disks. The unsettling consequence of a black hole's gravity is time dilation, a core prediction of Einstein's theory of relativity. Time is not a universal constant. It is a malleable fabric that is stretched and warped by gravity and velocity. The closer one gets to a massive object, the slower time passes relative to a distant observer. Near the event horizon of a black hole, this effect becomes extreme. Imagine a brave spacecraft, the Endurance, on a mission to observe a black hole up close. It positions itself in a stable orbit just outside the event horizon. For the astronauts on board, time would feel normal. Their clocks would tick second by second. But for mission control back on Earth, watching through a video link, something bizarre would happen. The signals from the ship would slow down. The astronauts' movements would appear to become glacial, their speech an endless, deep drawl. Each second for the crew would correspond to years, decades, or even centuries passing on Earth. If they were to hover at the very precipice of the event horizon, from the perspective of the outside universe, their time would appear to stop completely. They would be frozen in that final moment for all eternity, their image perpetually redshifted and fading. The Endurance would become a ghost ship, a permanent monument on the edge of infinity. This is not an illusion. It is the real nature of space-time. A journey to a black hole is a one-way trip not just in space, but into the future of the universe. Embedded within the mathematics of general relativity are even more fantastical possibilities. One of the most famous is the Einstein-Rosen bridge, commonly known as a wormhole. The equation suggests that the intense curvature of space-time at the heart of a black hole could, in theory, connect to another region of space-time, potentially forming a shortcut, a tunnel through the cosmos. One end of this tunnel would be the black hole, the point of entry. The other end, a theoretical white hole, would be a region of space-time from which matter and energy can only erupt, the antithesis of a black hole. This would create a bridge connecting two distant points in our universe, or even more speculatively, connecting our universe to another entirely separate universe. However, there are monumental problems. The primary issue is that the wormholes predicted by classical general relativity are incredibly unstable. They would collapse into a singularity in an instant, far too quickly for anything, even information, to pass through. To be traversable, a wormhole would require the existence of a form of exotic matter with negative energy density, something which theoretically exists in the quantum realm as the Casimir effect, but on a scale required to prop open a cosmic tunnel, it remains firmly in the domain of speculation. Yet, the idea is so powerful that it has become a staple of science fiction and a serious area of theoretical research, representing the ultimate to one of the most pervasive and compelling conspiracy theories surrounding black holes: the idea that they are not tombs, but portals. This theory, popular in ufology and certain ancient astronaut circles, posits that advanced extraterrestrial civilizations, or perhaps even our own far future descendants, have mastered the technology to stabilize wormholes. In this narrative, black holes are not the end of a journey but the beginning, the ultimate stargates. Proponents point to the mysterious disappearances of objects and the theoretical potential of wormholes as evidence that this could be possible. They suggest that the key lies in manipulating higher dimensions or harnessing the energy of spinning black holes. While this remains firmly in the realm of fantasy with no scientific evidence to support it, the theory persists because it taps into a deep-seated human desire for connection and exploration, transforming the ultimate symbol of death and oblivion into a gateway to new worlds and new civilizations. It is a powerful testament to how black holes capture not only our scientific curiosity but also our deepest myths and aspirations. The final, and perhaps most profound, concept emerging from the edge of black hole physics is the holographic principle. This is not a single theory but a radical paradigm shift in our understanding of reality itself. It was born from the work of physicists like Gerard T. Hooft and Leonard Susskind, who are grappling with the black hole information paradox. The principle proposes a truly mind-bending idea that all the information describing a three-dimensional volume of space, like the interior of a black hole, can be entirely encoded on a two-dimensional surface that bounds that volume, such as the event horizon. Imagine a hologram on your credit card, a two-dimensional surface that creates the perfect illusion of a three-dimensional image. The holographic principle suggests our perceived three-dimensional universe might be a similar illusion, a vast and complex hologram projected from the information stored on a distant, two-dimensional surface. In the context of a black hole, It means that every particle, every bit of energy that falls in, is not lost inside the singularity. Instead, its information is smeared and stored as infinitesimally tiny bits on the event horizon, dramatically altering our picture of the black hole's interior. This principle, if correct, would mean that the universe we experience is fundamentally a projection, and that the ultimate reality exists on a thin, distant shell. It is a concept that blurs the line between physics and philosophy, suggesting that the monsters we study are not just physical objects, but perhaps the most complex informational structures. General relativity versus quantum mechanics. For decades, the two foundational pillars of modern physics, Einstein's theory of general relativity and the framework of quantum mechanics, have existed in a state of peaceful coexistence but fundamental tension. One governs the cosmos on its grandest scales, the dance of galaxies, the curvature of space-time, the nature of gravity itself. The other governs the subatomic world, a bizarre realm of probability, uncertainty, and ghostly connections. Each is spectacularly successful in its own domain, but they are mathematically and philosophically incompatible. The place where this Cold War turns hot, where the two theories meet and their contradictions become irreconcilable, is at the event horizon of a black hole. This chapter explores the battlefield and the conceptual revolutions it has sparked. The first and most famous salvo in this war was fired by Stephen Hawking in 1974. Applying quantum field theory to the curved spacetime around a black hole, he made a shocking prediction. Black holes are not perfectly black. Due to weird quantum effects occurring just outside the event horizon, they should slowly leak radiation and evaporate over astronomical timescales. The process, now known as Hawking radiation, works like this. According to quantum mechanics, empty space is not truly empty. It is a seething foam of virtual particles, particle and antiparticle pairs that constantly pop into existence and, almost instantly, annihilate each other. This is a proven phenomenon known as quantum fluctuation. Hawking realized that if such a pair appears right at the event horizon, a bizarre thing can happen. One particle falls into the black hole, while its partner escapes into space. To conserve energy, the particle that falls in must have negative energy. This effectively reduces the mass of the black hole. The escaped particle, now a real particle, carries positive energy away into the universe. From a distant observer's perspective, the black hole has just emitted a particle. Over time, this slow, steady trickle of radiation causes the black hole to lose mass and, eventually, after periods of time so vast they are almost meaningless to the human mind, evaporate completely. This was a monumental discovery, elegantly marrying quantum mechanics with gravity, but it immediately created a crisis that would shape physics. This crisis is known as the black hole information paradox, and it is arguably the most important and vexing problem in theoretical physics. The conflict is stark. Quantum mechanics is built on a fundamental principle. Information is never lost. The universe is unitary. If you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any point in the past or future. Every interaction is, in a sense, reversible. General relativity, in the context of a black hole, seems to blatantly violate this. When an object, say, a book or an entire star, falls into a black hole, it is torn apart and crushed into the singularity. According to classical general relativity, all the information about that object, what atoms it was made of, its structure, whether it was a book by Shakespeare or a lump of coal, is utterly and permanently destroyed when the black hole evaporates via Hawking radiation. The radiation itself is purely thermal. It is random noise, a featureless hiss containing no information about what fell in. This presents an unacceptable either-or choice. Either our understanding of quantum mechanics is wrong and information can be destroyed, or our understanding of general relativity is wrong and something must happen to preserve the information. Most physicists side with quantum mechanics, believing the information must be preserved, but the question of how has spawned decades of intense debate. One of the most dramatic proposed solutions to the information paradox is the firewall paradox. Imagine an astronaut falling towards a black hole's event horizon. According to Einstein's principle of equivalence, the cornerstone of general relativity, the astronaut should feel nothing special upon crossing the horizon. It is a smooth, uneventful passage through a one-way membrane. However, calculations by a group of physicists in 2012 showed that for the information to be preserved, this cannot be the case. To ensure that the outgoing Hawking radiation carries information, The quantum fields at the event horizon must be in a special, highly energetic state. This would mean that the event horizon is not a tranquil place, but a searing wall of fire, a firewall, that would instantly incinerate any object falling into the black hole. The firewall paradox forces physicists to choose between three deeply cherished principles: the unitarity of quantum mechanics, information is not lost; the equivalence principle of general relativity, freefall is smooth; and locality, physics happens at a point. You can save two, but not all three. The existence of a firewall would mean that the event horizon is a physically destructive boundary, fundamentally altering our picture of a black hole's interior and violating the very principles that predicted black holes in the first place. A profoundly elegant potential solution is the ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind. This idea is so beautiful it seems almost too good to be true. It connects two seemingly unrelated concepts: wormholes and quantum entanglement. ER refers to the Einstein-Rosen bridge, or a wormhole, a tunnel through spacetime connecting two distant points. EPR refers to the Einstein-Podolsky-Rosen paradox, which describes quantum entanglement, the spooky action at a distance where two particles are linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. The ER equals EPR conjecture boldly proposes that these are not two different phenomena, but two different descriptions of the same thing. A pair of maximally entangled particles, according to this idea, are secretly connected by a microscopic wormhole. This provides a stunningly geometric picture for how information might escape a black hole. When a black hole forms and then evaporates, the Hawking radiation particles it emits become entangled with the black hole's interior. If ER equals EPR is correct, then these entangled particles are connected by tiny wormholes. The information about what fell into the black hole isn't stored on the horizon or burned up at a firewall. It is transmitted through these quantum wormholes to the outside radiation. This suggests that space-time itself may not be a fundamental backdrop of the universe, but rather an emergent property that arises from a vast, underlying network of quantum entanglement. The black hole, in this view, is not a destroyer of information but a processor of it, and its interior may be far more complex and interconnected with the outside universe than we ever dreamed. Black holes as architects of the universe. For centuries, black holes, inasmuch as they were considered at all, were envisioned as the ultimate endpoints of cosmic evolution, destructive voids, final resting places for matter and light. However, one of the most profound shifts in modern astrophysics has been the realization that black holes are not merely passive consumers. They are, in fact, dynamic and powerful engines that play a crucial, creative role in shaping the universe on the largest scales. From regulating the birth of stars to seeding the cosmos with the elements for life, black holes are the unsung architects of the cosmic landscape, their influence extending far beyond their event horizons. The most significant demonstration of this architectural power is the intimate connection between supermassive black holes and their host galaxies. For a long time, the correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole was a curious but unexplained fact. We now understand this is not a coincidence. It is evidence of a deep, symbiotic, and often violent relationship, a process known as feedback. A supermassive black hole at the heart of a galaxy acts as a cosmic regulator. When a galaxy is rich with gas, this material funnels toward the center, feeding the black hole and igniting an active galactic nucleus, AGN, a quasar that can outshine the entire galaxy. As the black hole feasts, it doesn't do so quietly. The immense energy released powers colossal winds and, most importantly, those relativistic jets that we discussed earlier. These jets blast outwards, injecting tremendous energy into the surrounding galactic gas. This energy heats the gas, preventing it from cooling and collapsing to form new stars. In some cases, the feedback is so powerful it can blow away the galaxy's entire reservoir of star-forming gas, effectively shutting down star formation for eons. This process explains why massive, elliptical galaxies are often red and dead, filled with old stars and devoid of the young, blue stars seen in spiral galaxies. The black hole, through its violent activity, has quenched its own galaxy's growth. It is a self-regulating mechanism. The galaxy feeds the black hole, and the black hole, in turn, governs the galaxy's evolution. Without this feedback, galaxies would likely be much larger, brighter, and more chaotic. Beyond this grand-scale regulation, black holes are also the universe's ultimate recyclers. The popular imagination holds that matter falling into a black hole is lost forever. But this is only a partial truth. While the material that crosses the event horizon is indeed gone from our universe, the vast majority of matter drawn towards a black hole never actually makes it across. Instead, it gets caught in the powerful, swirling accretion disk. Here, in this maelstrom of superheated plasma, matter is subjected to immense frictional and tidal forces, as well as being bombarded by intense radiation from the inner disk and the black hole's jets. This environment is a crucible of nuclear transformations. Through processes of spallation and fragmentation, heavier atomic nuclei are shattered and reassembled into new, lighter elements. Furthermore, the relativistic jets act as colossal particle accelerators, far more powerful than anything we can build on Earth. They smash particles together at near-light speeds, potentially forging rare and heavy elements. When these jets collide with the interstellar medium or when material is blown out by the black hole's winds, these newly forged elements are launched far out into the galaxy and beyond, enriching the intergalactic medium. The iron in your blood, the gold in a wedding ring, the uranium in a power plant. While originally forged in stellar explosions, a significant portion of these heavy elements may have received their final processing in the violent, energetic outflows from black holes. They are not just tombs, they are also furnaces, scattering the atomic seeds for future planets and, potentially, life itself. This creative destruction extends to the very structure of the cosmos. The energy released by supermassive black holes, particularly in the form of their jets, is so immense that it doesn't just affect their host galaxy. It shapes the entire galaxy cluster they reside in. At the centers of many massive galaxy clusters, vast cavities have been observed in the hot, X-ray emitting gas that fills the space between galaxies. These cavities are precisely aligned with the radio lobes created by the black hole's jets. The jets are essentially inflating gigantic, cosmic bubbles in the intracluster medium, pushing the gas aside and preventing it from cooling and flowing into the central galaxy to form trillions of new stars. This AGN feedback at the cluster scale is essential for solving the cooling flow problem, where theoretical models predicted far more cool gas and star formation in cluster centers than is actually observed. The black hole's activity provides the necessary heating to maintain balance, effectively setting a thermostat for the entire cluster and governing the growth of the most massive galaxies in the universe. In this role, black holes function as the master architects of the large-scale structure of the cosmos, their influence spanning hundreds of thousands. The era of black holes. Our journey thus far has taken us through the birth, anatomy, and cosmic influence of black holes in the present-day universe. But to truly comprehend their ultimate nature, we must project our gaze forward across timescales so vast they defy human comprehension. We must venture into the far future of the cosmos, a period where black holes will no longer be mere features of the universe, but will become its dominant characters, its final rulers, and ultimately, its silent witnesses to the heat death of all things. The universe's current era, in which we are fortunate to live, is known as the stelliferous era, the age of stars. It is a time of light and structure, where galaxies blaze with stellar nurseries and suns sustain planets. But this is a temporary, albeit brilliant, phase. Over the next trillion years, the last reserves of interstellar gas will be consumed, and the process of star formation will sputter and halt. The most massive stars will have long since died in supernovae, and the longer-lived, smaller stars, the red dwarfs, will slowly burn through their fuel, their faint red glow eventually fading to black. The galaxies, devoid of new stars, will begin to dim. The universe will enter a long, slow twilight. In this darkening cosmos, the objects that will inherit the universe are the stellar remnants, the cold, dead cinders of white dwarfs and neutron stars, and the far more massive and influential black holes. They will become the gravitational anchors of a dark, post-stellar cosmos. During this epoch, known as the degenerate era, black holes will begin their reign in earnest. While the universe expands and cools around them, black holes will slowly, inexorably, grow. Their immense gravity will act as cosmic vacuum cleaners, drawing in the scattered, cold remnants of this dead era, the rogue planets, the brown dwarfs, the diffuse gas and dust that still drifts in the void. A stellar mass black hole, wandering through the corpse of its former galaxy, could, over eons, double or even triple its mass through this slow, cold accretion. The supermassive black holes at the galactic centers will also feast, pulling in the degenerate stellar remnants that slowly spiral inward due to the emission of gravitational waves. the universe will become a much darker, quieter, and simpler place. Its dynamics governed almost entirely by the silent, relentless pull of these dark giants. This reign is not eternal. Thanks to Stephen Hawking's revolutionary insight, we know that black holes are not permanent fixtures. They possess a temperature, albeit an infinitesimally low one for large black holes, and they must therefore radiate energy. This Hawking radiation, as we have explored, is a quantum mechanical process that causes a black hole to slowly lose mass. For nearly all of a black hole's life, this process is negligible. A stellar mass black hole loses so little energy that it would take a timescale longer than the current age of the universe to evaporate even a fraction of its mass. But in the far, far future, as the universe cools towards absolute zero, this slow leak becomes significant. The evaporation rate is inversely proportional to the mass. As the black hole loses mass, it gets hotter and evaporates faster. The final moments of a black hole's life are not a slow fading, but a runaway explosion. When a black hole's mass has been reduced to around that of a small mountain, its temperature would rise to millions of degrees, and it would be emitting energy at a prodigious rate, primarily in the form of gamma rays and other high-energy particles. The final 0.0001% of its mass would be converted into energy in a violent, instantaneous burst, a brilliant, final flash of light in an otherwise dark and cold cosmos. A stellar mass black hole might take 10 to the power of 67 years to evaporate. A supermassive black hole like Sagittarius A** could take 10 to the power of 87 years or more, numbers so large they have no physical analogy in our experience. This profound fate leads to one of the most speculative and fascinating ideas in theoretical physics, the concept of a Boltzmann brain. In an infinitely expanding, eternally existing universe that reaches a state of maximum entropy, a heat death, random quantum fluctuations will, given enough time, eventually create any physically possible configuration of matter. It is statistically far more likely for a single, self-aware brain to spontaneously form from the quantum foam, complete with false memories of a past life in a universe that no longer exists, than for the entire, complex universe we see around us to spontaneously fluctuate into existence. If our current understanding of cosmology and the ultimate evaporation of black holes is correct, then the universe will eventually reach a state where the only events that occur over near-infinite timescales are these random fluctuations. Therefore, the statistical probability is that you, the observer, are far more likely to be one of these random, disembodied Boltzmann brains than a person living in the universe's brief, early, low-entropy stelliferous era. This is a deeply unsettling philosophical paradox that arises directly from our projections of the far future, a future dominated and then vacated by black holes. Before this ultimate fate, a sufficiently advanced civilization might see black holes not as tombs, but as the ultimate resource for survival and transcendence. The Penrose process, which we touched on earlier, provides a theoretical mechanism to extract the rotational energy of a Kerr black hole. A Type 2 or 3 civilization on the Kardashev scale, facing the cooling of the universe, could use this process to power their civilization for eons. They could construct a Dyson sphere not around a star, but around a black hole, capturing not just the Hawking radiation but the vastly more significant energy from the accretion of matter and the Penrose process. Furthermore, the theoretical possibility of closed time-like curves in the vicinity of a rotating black hole, while fraught with paradox, suggests that black holes could be the key to manipulating time itself. A far future civilization might use a black hole as a gravitational slingshot for interstellar travel, or even attempt to engineer it into a stable wormhole, a last-ditch escape from a dying universe into a younger one. In the final chapters of cosmic history, black holes could transform from symbols of oblivion into the last beacons of hope and power for any intelligence that remains. They are the final batteries, the ultimate computers, and potentially, the last doors out of a darkening room. The unexplained and the conspiracy theories. After our journey through the hard science and the far future fate of black holes, we now arrive at a frontier where established physics blurs into mystery, and mystery, in turn, fuels speculation and conspiracy. This is the realm of the unexplained, where the limits of our knowledge create a vacuum filled with tantalizing puzzles and compelling, if unproven, narratives. To fully understand the cultural and scientific phenomenon of the black hole, we must venture into these shadowy territories, examining the lingering questions that perplex physicists and the radical theories that capture the public imagination. One of the most persistent and legitimate mysteries in cosmology is the true nature of dark matter. This invisible substance makes up about 85% of all matter in the universe. its presence betrayed only by its gravitational pull on galaxies and galaxy clusters. While the leading candidates are exotic subatomic particles like WIMPs, weakly interacting massive particles, the door has never been closed on the possibility that a significant portion of dark matter could be made of primordial black holes, PBHs. The appeal of this theory lies in its simplicity. It requires no new physics beyond general relativity and the conditions of the early universe. If a vast population of asteroid mass PBHs were to permeate the cosmos, they would be virtually invisible yet would exert the precise gravitational influence we attribute to dark matter. However, this massive compact halo object hypothesis has been severely constrained by observations. Microlensing surveys, which watch for the temporary brightening of a star when a dark object passes in front of it, have largely ruled out PBHs in a wide mass range as the primary constituent of dark matter. Yet, a window remains open for PBHs of certain, very specific masses. The mystery endures, and the hunt continues, with the tantalizing possibility that the dark matter halos enveloping galaxies are, in fact, swarms of ancient, primordial black holes. The theoretical war over the black hole information paradox, which we detailed earlier, remains unresolved. While ideas like the holographic principle and ER=EPR offer elegant potential solutions, they are not yet proven. The central conflict, how to reconcile the smooth spacetime of general relativity at the event horizon with the information-preserving requirements of quantum mechanics, is the single greatest crisis in theoretical physics. The firewall paradox starkly illustrates that our current understanding is incomplete. Is the event horizon a placid point of no return or a searing wall of energy? The very fact that such a radical and violent solution is even on the table demonstrates how deeply we are still struggling to understand the nature of reality at this boundary. This isn't just an academic debate. Its resolution is seen as the essential stepping stone to a theory of everything, a unified framework that would describe all the forces of nature. The black hole is the ultimate arbiter in this quest, and it has not yet yielded its final secret. This fertile ground of unresolved mysteries gives rise to more speculative and popular theories. One of the most enduring is the Nemesis or Planet X hypothesis, which posits a hidden, massive body in the outer reaches of our solar system, perturbing the orbits of distant trans-Neptunian objects. While most discussions center on a hypothetical planet, a more exotic variant suggests this object could be a primordial black hole. A PBH with a mass of 5 to 10 Earths would be only about the size of a grapefruit, yet its gravitational pull would be identical to a planet. This would elegantly explain why, despite extensive searches, no large planetary body has been found. It is a dark, compact ghost in our own cosmic backyard, its presence inferred only by the subtle, gravitational tugs on the frozen worlds at the edge of our vision. While the evidence for any such object is still highly contested within the astronomical community, the theory showcases how black holes can provide alternative explanations for observed phenomena, pushing the boundaries of what we consider possible in our own celestial neighborhood. Perhaps the most captivating conspiracy theory, popularized by science fiction and ancient astronaut proponents, is the idea that black holes are not natural phenomena but engineered structures, stargates created by advanced civilizations for interstellar or even interuniversal travel. This theory twists the legitimate, though highly speculative, physics of wormholes, Einstein-Rosen bridges, into a technological narrative. Proponents ask, if a naturally occurring wormhole is unstable, could a Type 3 civilization with godlike command over energy and matter at galactic centers be these stabilized portals, nodes in a vast, cosmic transportation network? They point to the mysterious, high-energy signatures of active galactic nuclei as potential evidence of this technology in use. While there is not a shred of empirical evidence to support this, and the energy requirements are fantastical beyond comprehension, the theory persists because it fulfills a deep human archetype, the transformation of a symbol of death into a gateway to new life and exploration. It is a myth for the space age, turning the ultimate cosmic monster into a tool of transcendence. Finally, we have the most profound cosmological conjecture of all, that our own universe is the interior of a black hole existing within a larger meta-universe. This idea, while fringe, is mathematically plausible. The conditions of the Big Bang, a singularity of infinite density, are eerily similar to the singularity inside a black hole. Some models suggest that the collapse of a massive star in a parent universe could trigger the creation of a new, expanding universe within its black hole, with its own laws of physics. This theory of cosmological natural selection, proposed by Lee Smolin, suggests that universes that produce more black holes are more fertile, spawning more daughter universes. Over cosmic generations, this would lead to universes, like our own, that are fine-tuned for black hole production. It is a grand, cyclic, and awe-inspiring vision where black holes are not the end, but the beginning. They are the wombs of new cosmic realities, making our entire universe a single link in an infinite chain of cosmic genesis. This idea, more than any other, elevates the black hole from a destructive curiosity to a fundamental, creative force in the multiverse. Why black holes matter? We have journeyed together to the edge of reality and peered into the abyss. We have witnessed stellar suicides that birth monsters, dissected the anatomy of nothingness, and traced the invisible hand of gravity as it sculpts galaxies. We have fast-forwarded to the end of time and entertained the wildest speculations of science and conspiracy. Now, as our documentary draws to a close, we must step back from the equations and the event horizons to ask the most human of questions. After all this, what does it mean? Why do these dark, distant objects, these cosmic vampires, matter to us, here and now? First and foremost, black holes are the universe's ultimate laboratory. They are the only environments where the two great pillars of 20th century physics, Einstein's theory of general relativity and the quantum mechanics of Bohr, Heisenberg, and Schrödinger, are forced to confront one another. In our terrestrial labs, we can study these theories in isolation, but at the event horizon of a black hole, their peaceful coexistence shatters. The smooth, geometric fabric of spacetime demanded by relativity clashes violently with the fuzzy, probabilistic, and information-preserving world of the quantum. The black hole does not care about our intellectual divisions. It simply is. And in its stark existence, it presents us with a series of paradoxes, the information paradox, the firewall paradox, that are not flaws in our theories, but rather signposts. They are glaring indicators that a deeper, more profound truth lies just beyond our current grasp, a theory of quantum gravity that will unite the very large and the very small. To study a black hole is to engage in the most fundamental form of inquiry, to probe the very rules that govern reality. Every observation, from the shadow of M87* to the chirp of a gravitational wave, is an experiment conducted in this grand, natural laboratory, testing our understanding of the cosmos at its most extends far beyond the realm of theoretical physics. They serve as the ultimate cosmic mirror, reflecting back to us a humbling perspective on our place in the universe. We live on a fragile, pale blue dot, orbiting an average star, in the quiet suburbs of a spiral galaxy. Our daily concerns, our triumphs, and our tragedies, while deeply meaningful to us, play out on a stage that is almost infinitesimally small in the cosmic drama. Black holes remind us of the raw, untamed, and overwhelming power of nature. They are entities that can tear stars apart, that can freeze time, that can erase information from the universe. They force a cosmic perspective, what some call the overview effect, but on a far grander scale. They are a testament to the fact that the universe is not designed for our comfort or comprehension. It is a place of sublime beauty and terrifying violence, and we are privileged, for a brief moment, to be aware of it. This journey through the science and mystery of black holes also reveals a profound truth about human nature, our insatiable drive to explore and understand. The black hole story is a saga of human curiosity triumphing over impossibility. It began as a ghost in the equations of a single man, Einstein. It was pursued by theorists like Oppenheimer, Wheeler, and Hawking, who dared to imagine the unimaginable. It was confirmed by observers and engineers who built telescopes to see the invisible and instruments to listen to the whispers of spacetime itself. We are a species that looked at a void and refused to see nothing. We saw a question, and we have spent a century devising ever more ingenious ways to answer it. This relentless pursuit of knowledge in the face of such a formidable subject is a celebration of the human spirit. It demonstrates that our minds, though confined to this planet, can comprehend the dynamics of objects millions of light years away, whose very nature defies concept. Have transformed in our understanding. They are no longer just the monsters of cosmology, the ultimate predators in the cosmic food chain. We have come to see that they are also creators and architects. They regulate the growth of galaxies, they forge and scatter the elements of life, and they may even be the wombs of new universes. They are the nexus where destruction and creation are inextricably linked, where the end of one thing becomes the beginning of another. They teach us that in the grand, cyclical story of the cosmos, death, and rebirth are part of a single, continuous process. As we conclude, let us return to the words of the visionary who first saw their light in the darkness. Stephen Hawking ultimately reimagined their nature, stating, "Black holes ain't as black as they are painted. They are not the eternal prisons they were once thought. Things can get out of a black hole, both to the outside, and possibly to another universe. So if you feel you are in a black hole, don't give up, there's a way out." He was speaking not just of physics, but of the human condition. The story of the black hole is a metaphor for our own encounter with the unknown. It is a narrative that tells us that even from the darkest, most inescapable seeming places, whether they be in the cosmos or in our own lives, information is not lost, energy can be found, and new pathways can emerge. They are the ultimate symbols of mystery, yes, but they are also, paradoxically, beacons of understanding. They remind us that the universe is far stranger, more wonderful, and more interconnected than we ever dared to dream. And our quest to understand them is one of the most beautiful and profound stories we have ever told ourselves about the world we call home. Our journey reaches its end. We have descended into the heart of darkness and emerged with a new vision of the cosmos. We have learned that black holes are not mere voids, but the gravitational graves of massive stars, born from the most violent explosions in the universe. We have dissected their anatomy, from the point of no return at the event horizon to the space-time shattering singularity at their core. We have seen how these invisible monsters are found, by the screams of the matter they consume, by the frantic dance of stars around them, and by the revolutionary ripples in space-time they create when they collide. We have explored their cosmic role as architects and alchemists, regulating the growth of entire galaxies and seeding the universe with the elements of life itself. We have grappled with the mind-bending physics they inspire, from the slow death of Hawking radiation to the holographic principle, which suggests that our reality may be a projection on a distant, two-dimensional surface. And we have looked to the far future, to a time when black holes will be the last sentinels of a dark and cooling cosmos, before they too vanish in a final flash of light. From the infinitely small to the infinitely large, black holes have taught us that the universe is stranger, more violent, and more beautifully interconnected than we ever imagined. They are the ultimate teachers, showing us where our knowledge ends and the next great mystery begins. We sincerely hope this journey through space and time has brought wonder and peace to your evening. If this story resonated with you, if you enjoy getting lost in the deepest mysteries of the cosmos, please support our channel. Your engagement is what allows us to continue this exploration. Subscribe to Heavenly Sleep Stories so you don't miss our next adventure. Give this video a like to let us know you want more content like this. Share your thoughts in the comments below. What was the most astonishing thing you learned? And most importantly, what other cosmic mysteries should we explore next? The lost libraries of ancient Alexandria? The enigmatic power of neutron stars? The search for a theory of everything? Thank you for listening. Thank you for your curiosity. From all of us at Heavenly Sleep Stories, may your dreams be filled with the wonders of the universe. Good night.